Okay, so the first thing we're going to do is we're going to factor our rational function like we did yesterday, and we're going to reduce it if possible. If it reduces, remember that's where you would get a hole in the graph, and actually the hole will plot at the very, very end, but you want to make a note if you have one at the beginning. Then we're going to find x and y-intercepts, so that's just review. X-intercept, you plug in 0 for y, y-intercept, you plug in 0 for x, and that'll give us a couple points on our graph. Then we're going to find vertical, horizontal, maybe even oblique asymptotes like we practiced yesterday. Vertical are going to come from your domain restrictions, your denominator. Horizontal, we're going to compare those n's and m's. And oblique is one of those cases as well with the n's and m's. And then if from that information you don't have enough that you feel like is able to give you a nice picture of it without a graphing calculator, you can use test points, so just extra points between your asymptotes to plot, so you can kind of see where the graph is located, and then we'll make a sketch from there. Okay. So I think the first one or two is not on your big idea worksheet, but we'll get to that one today. So in your notebook, if you just want to do these first couple graphs, that would be fine. Okay, so let's do all these steps with a couple problems so you can see what these look like. First one we're going to graph is f of x equals x times x minus 1 over x minus 1 times x squared minus 9. Okay, so it's factored a little bit for us here already. Does anything factor any further on this one? Yes, x squared minus 9 factors to what? It's going to be difference of squares, yep. So x minus 3 and x plus 3. There we go. Okay. And what do you notice about the factors that we see there? One of them cancels. So we can make it x over x minus 3, x plus 3. Okay. That also means at that x minus 1, if I set that equal to 0, we're going to get a hole in the graph. And we'll graph the hole at the very end. The hole appears where x minus 1 equals 0. So at x equals 1, we'll have a hole in the graph. Okay? All right. So now, first thing we can find are intercepts. Let's start with a y-intercept. How do you find a y-intercept? X is 0. So I'll just use the factored version that we have at the end there. 0 over 0 minus 3, 0 plus 3. Well, 0 divided by anything is going to give me 0. Okay, so that's my y-intercept. I'm just going to plot things as I go here. Y-intercept at 0 is going to be a point on the origin. To get x-intercepts, you're going to set your function equal to 0, your y equal to 0, which is going to look like 0 equals x over x minus 3, x plus 3. To solve for x, the first thing that you're going to do is make this an easier equation. And to make it an easier equation, we multiply both sides by the denominator. And something special is going to happen every time you do this. On the right side, if I multiply the denominator, denominator cancels. On the left side, when you're doing this, it's always 0. So if I multiply 0 times anything, what am I going to get? 0. So when you're finding an x-intercept, it doesn't actually matter what the denominator is, because in the first step, it's going to go away every time. It's really your numerator. If your numerator equals 0, your function equals 0, because 0 divided by anything is 0. So you can make a little note to yourself here for x-intercept. Just your numerator equal to 0 is enough to find those x-intercepts. That will save you a step. Okay, just numerator equal to 0 will be fine for these. And so for this one, if I set my numerator equal to 0, I get x equals 0, which is not a shock because I already had that point at the origin. Okay, but maybe that would give us some other ones for different problems. All right, now review from yesterday. Vertical asymptotes. occur where your denominator is equal to 0? Well, my denominator is already factored at x minus 3x plus 3, so what are the vertical asymptotes? Set those equal to 0, you're going to get x equals positive 3, x equals negative 3, get in the habit of putting x equals in front of those. So I'm going to sketch those. At negative 3 and at positive 3, we have vertical asymptotes. Remember, vertical asymptote is a domain restriction, so we are never, ever, ever going to cross these lines. Okay. Then horizontal and oblique kind of go together. Let's compare our n's and our m's. What is n, degree of the numerator? And by the way, you can look at the original problem or the reduced one. The relationship is going to be the same, whether they're equal to, greater than, or less than, because when we cancel, it just changes the degrees by the same amount. So degree, you could say, of the numerator is 1. Degree of the denominator is 2. We're looking at the reduced one. So n is less than m. If n is less than m, which of the cases was it? Do you remember from yesterday? You have a horizontal asymptote at 0, y equals 0, or the x-axis. Okay, which means if I ask you for an oblique asymptote, your answer is none. There's only one or the other. So if we have a horizontal asymptote, we do not have an oblique asymptote. Okay, so I'm going to sketch that. So on the x-axis, I'm going to make my dashed line. Remember, it is okay to cross a horizontal asymptote, especially in the middle. That's going to happen often. Okay, but on the ends, we're going to approach it. All right, so now we have to figure out where all the little branches are located at, and this is where a table of values is helpful. So I'm going to make a little XY table. And what I want to do is I want to pick numbers in the regions that I've kind of created from this graph. I want to pick something to the left of -3. I want to pick something between -3 and 0. I want to pick something between 0 and 3, and I want to pick something greater than 3. I want to pick something in each region so I have some points, and then you could always pick more than that, but I would say that's probably the bare minimum. So numbers smaller than -3, I'm just going to use -4. A number between -3 and 0, I'm going to use -1. A number between 0 and 3, I'm going to use 1. And a number greater than 3, I'm going to use 4. Okay, and then we're just going to plug those in to the function. Now, you can use the reduced one. I actually think if I look at the unfoiled version, like x squared minus 9 in the bottom, it might be easier to plug in my head or in your calculator, but you can use either. Let's say I plug in -4. -4 in the numerator is just -4. -4 in the denominator is going to give me what? -4 squared minus 9. -4 squared is 16 minus 9, 7. Okay, 7? Yeah, okay. All right, and -4 sevenths doesn't reduce, so I'm just going to leave it. -1 in the numerator, -1. -1 in the denominator is 1 squared, 1 minus 9. -8, -1 over -8, 1/8, positive 1/8. Okay, plug in 1 in the numerator, 1. 1 in the denominator is -8, so -1/8. 4 in the numerator, 4. 4 in the denominator again gives me 7. 4 sevenths doesn't reduce. So see how I'm just doing those in separate pieces and then reducing at the end if you need to. You don't need to make it crazy. All right, let's plot those points. At -4, I'm at -4 sevenths below the horizontal asymptote. At -1, I'm at positive 1/8. And at positive 1, I'm at -1/8. And at positive 4, I'm at 4 sevenths. Now here's what these graphs will usually look like. And when I say usually, I mean 99% of the time. Occasionally there's going to be a weird one, but we're not going to know that anyway when we're just sketching it. On the far left and the far right, you're going to get these branches that kind of look like L shapes. They're going to be kind of contained by the asymptotes you've graphed. They will either be below or above, but not both, because if they were above and below, it wouldn't be a function. It wouldn't pass the vertical line test. So this point alone is enough to tell me that I'm going to have a branch in kind of like this little quadrant I've created. So it's going to be down here. Don't touch those asymptotes. Okay? And then on the far right, same thing. That point above the axis is enough to tell me that that branch is going to be kind of contained on top. Now in the middle, one of two things is usually going to happen. It's going to look like one of our power functions where both ends go down and both ends go up, or cubic going up or cubic going down. Now you guys should be able to see from this, it looks like it's going up on this side and down on this side. So it's going to look like a cubic function going down, but it's one of those four power function shapes that we talked about when we were talking about end behavior with your polynomials is what these look like. So it's going to look something like that. And if you are unsure about connecting the dots, do like you do with anything else, just plot more points. The more points you plot, the more accurate your graph is going to be. And if you're unsure about a certain area, just pick some more points in that area until it looks good. And then when you guys are doing this at home, of course, you can then put this in your calculator and check the graph. Okay, on Math Excel, these are mostly going to be matching for the graphs and stuff, but when you get to the test, you will have to do one of these on Friday, actually, by hand, all these little pieces. Okay, questions on that one? Okay, now this one, is this one on your big idea worksheet? Do you think you guys can try it? Maybe? Okay, I'll leave this up on the board for you. You can look at my work if you need to. I want you to try to, oh, we forgot about the hole. Oh, wait. We forgot about the hole. There's a hole at 1. So at x equals 1, there's going to be an open circle on that line I made. Because we had the hole. So it's going to look like that. It's just an open circle right in the middle of the curve at whatever x value the hole's located at. Whew, almost forgot that. That would have been really bad. Okay, try the next one. Find all the pieces and parts. Reduce it. Find the hole if there is one. X-intercept, Y-intercept, vertical asymptotes, horizontal asymptotes, oblique asymptotes, plot some points, get a sketch, and if you get done early, check it with your calculator. See what it looks like. Go for it. Let me bring it up here and we'll talk about it. This one's a little weird. So before you panic on that right side, if you have a curve down here, I would not mark it wrong, okay, on this side. This one is very weird on the right side. It actually, if you plug in 2, you'll see that it equals, it equals exactly 1. It crosses the horizontal asymptote, and then actually it just kind of hovers right below it. So if you look at this graph in your graphing calculator, you'll see that horizontal asymptote at 1, but it actually goes right below it. But if you had plugged in like 3 or 4 or 5 or 6, you would have gotten a point below that horizontal asymptote and you would have sketched it with a branch down here. So I would not mark that wrong. And again, we're just sketching. So if that happened, that was okay. So other points that are on here, Y-intercept, you plug in 0. I just use the original numerator and denominator and I get 1/3. So that's the point on my y-axis. X-intercept, when you solve, you get plus and minus the square root of 1/2, which is about 0.7. So that gives me points on either side. Vertical asymptotes come from the denominator, which you can see I factored at -3/2. So that's that one on the left here. X equals 1 is the other one on the right. And then actually from the 3 points you have there and those 2 vertical asymptotes, it's enough to see that little power function in the middle that's going to go down on both sides. You really don't need any more points in this area in your table. Horizontal asymptote is y equals 1 because my degree of the numerator and denominator are both 2. And then that means I divide the leading coefficients, which also happen to both be 2 here, which is giving me y equals 1, which means I don't have an oblique asymptote. I plugged in -3, and I got a point above, so that gave me that branch. And then again, I kind of knew this one was going to be weird, but here's some example points you could have plugged in on that right side. Okay. What questions do you have on all the little pieces and parts here?
So you can't cancel 2 ones.
You cannot cancel out that 2x squared because it's not a common factor. So ask yourself this if you're going to cancel something. Could you factor it out? Could I factor out a 2x squared? The answer is no. So I can't cancel a 2x squared. Well, it's a common factor. Bless you. Other questions? Nothing cancels here, so there's no holes in the graph at the end you have to worry about. Okay, the last problem that we're going to do together, you can just do in your notebook. This one's going to have an oblique asymptote, which is not something that you're going to see like on a test that you're going to have to sketch by hand. Instead, this is something that you're going to just see in Math Excel when you do your homework, where you're going to have to find the oblique asymptote and then match it with your graphing calculator, okay? So I have f of x equals x cubed minus 1 over x squared. X cubed minus 1 over x squared. So finding the various pieces and parts here, I'm going to start with, does anything factor? And the answer is no here. Nothing in the denominator factors. I don't have any common factors. It's a cubic in the numerator. No factors, no canceling, no holes in the graph. All right, next I'm going to look at my y-intercept. My y-intercept is when x equals 0. Now, if I put 0 in this function in the denominator, what's going to happen? Am I allowed to divide by 0? No. So that means there is none, which means likely you actually have a vertical asymptote at 0. That would be what happens when you don't have a y-intercept. The y-axis is actually a vertical asymptote. You don't cross it. X-intercept, we just set our numerator equal to 0. And then we solve. So I'd add 1. 1 equals x cubed. Take the cube root. What's the cube root of 1? 1 is my x-intercept. Okay. Vertical asymptotes. If I set that denominator equal to 0, I get x equals 0. Again, not a shock. You can make your little, oh, mine's going to be a little crooked, but you get the idea. On the y-axis at x equals 0, we're going to have a vertical asymptote. We're not going to cross it. Now we look at horizontal and oblique. What's my n, degree of the numerator? M, degree of my denominator? 2, n is greater than m, which means if we ask for a horizontal asymptote, your answer would be none. Oblique asymptote, we calculate by doing the division now, and then we can sketch that. I have to divide x cubed minus 1 by x squared. Can I use synthetic division to do that? I cannot, because I'm dividing in an x squared. We have to use long division. So, long division, x cubed, I have a 0x squared, a 0x minus 1, and we are dividing in x squared. Remember, we're looking for the quotient here. The quotient is going to give me my oblique asymptote. All right, so a little review of long division. X squared times what gives me x cubed? X. X times x squared gives me x cubed. Subtract 0, 0, 0. Bring down my minus 1. And that's actually our remainder. Okay, so not a long division problem. We have a quotient of x, put a y equals in front of it. That is your oblique asymptote. Remember, the remainder is irrelevant. We do not use it. Y equals x, what shape is that if I were to graph it? It's the identity function. It's just our line that starts at 0 and has a slope of positive 1. So you can sketch that. Oblique asymptote, that diagonal line that's going to cross through our graph. And then at this point, once you have those, you would just type it in your calculator to see where the branches are located at. You could use test points here too, but we're not going to get crazy with it. So why don't you type it in your calculator real quick, and then you should be able to see why it's shaped like it is because of these asymptotes. I'm probably going to guess right now that because I have that x-intercept at 1, one of my branches is going to look like this. It's going to be contained there. We'll see what the other one looks like. Let's see. X cubed minus 1 divided by x squared. And the other one, yep, looks like that if you graph it. So those two parts in red are what you're seeing in the graphing calculator when you look at that picture. That's it. That is graphing rational functions, all the pieces and parts. That's the end of the chapter. Yay. All right, so last night you guys finished your 1517 Math Excel, right? Okay, 3-6 is due tomorrow night. So you have tonight and tomorrow to work on 3-6. I am going to give you right now your test review. Let's see here. Let's just stack the pins. All right. First part of your test is on Friday. Second part of your test is on Tuesday. Friday's part of the test. Friday's part of the test is basic calculator only. It is mostly over. Yes. Oh, thank you. It is mostly over that quiz you guys did a couple weeks ago and got back, the open note quiz, where you did like graphing the quadratic, graphing the polynomial, synthetic division, long division, like that stuff. That's on day 1 on Friday, plus one of these rational graphs. So there's only 5 questions on Friday. Actually, if you want to mark which ones they are, it's the first 3 on the front. Those 3 graphing problems are day 1. And then on the next page, it's the 2 at the top on the back side, where it says find all the zeros and determine if x minus 2 is a 0. So those 5 problems. There's not a little icon next to it for the graphing part. Okay? So I'm giving this to you now because you're going to have some options as far as review tomorrow. Tonight, I'm going to post the video of me going through these 5 problems. The solutions to those 5 problems are already on Polaris. If you guys want to try them on your own and check your answers, I will also post the video tonight. Tomorrow in class, you get to choose what you want to do. If you want to do these problems on your own and check your answers in class, do it. If you want to listen to Mrs. McDonald on the video lesson in class tomorrow and complete this with Mrs. McDonald, do it. I also have on Polaris and printed out all of those extra practice problems like we usually have. You can do those in class tomorrow if you want, and then I will be here to answer your questions on whatever. So if you feel like it is beneficial to watch a video, do it. If you feel like it's beneficial to try it and check your answers, do it. If you feel like you're good on this and you want to do the extra practice problems tomorrow, do it. Whatever works for you, however you want to prepare. All right, just those 5 for Friday. Monday, we'll do the same thing on the second part, getting ready for Tuesday. Okay? Questions on any of that? Awesome. All right. Cell phone lotto and we're done.